If I have seen further, it is by standing on the shoulders of giants. Newtonian mechanics is a theory that was established by English scientist Isaac Newton in the 17th century. Through mathematics and experiments, scientists in the 16th century, such as Galileo, began studying the motion of bodies. Newton followed the works of his predecessors, concluding and further developing their findings to eventually establish the theory of Newtonian mechanics. Newton obtained his bachelor's degree from the University of Cambridge at the age of 23. During the Great Plague, the university had to close temporarily, and he returned home. During those 2 years, he conducted private studies at home and discovered the law of gravitation, which is an important keystone of Newtonian mechanics. He also developed his theories on calculus and optics. The optical phenomenon of the white light of the sun is made up of different colors was discovered during this time. Newton explained to his friend Edmund Halley how mathematics could be used to determine the motion and elliptical trajectory of planetary orbits. Believing that this was a great scientific breakthrough, Halley persuaded Newton to publish his findings. The book, Mathematical Principles of Natural Philosophy, also known as Principia, was published in 1687 with Halley's encouragement and financial help. It can be regarded as one of the most important works in the history of science. Newtonian mechanics explains how a body moves or reacts when a force is applied to it. The theory covers the motion of a range of entities, including projectiles, celestial bodies, and the objects we encounter in our daily life. The Principia is an important doctrine in the history of natural science and has an extensive and profound impact on both natural science and philosophy. In this book, Newton considers and defines concepts such as mass, inertia, force, time, and space. He also engages in theories such as celestial mechanics and motions of the planets, the moon, and comets. But certainly, the most important of his discoveries are his 3 laws of motion. The law of inertia, the law of force and motion, and the law of action and reaction. Once we understand these 3 laws, we should be able to have some basic understanding of the motion of bodies. I have this idea. Since the Earth rotates from west to east, and assuming that I can find a way to float mid-air, for example, by staying in a hot air balloon up in the air, I will then be able to automatically move westward. I know this is wishful thinking, but why doesn't the idea work? Newton's first law of motion, also known as the law of inertia, states that an object at rest remains at rest, and an object in uniform motion remains in uniform motion unless acted upon by an external force. It seems, however, that the first law contradicts our daily experience. For example, if I remove my hand from this book, it will immediately stop moving. Our experience tells us that an object will eventually stop after being in motion for a while. The ancient Greek philosopher Aristotle said, "To keep an object in motion, a force needs to be applied continuously on the object." Surprisingly, this had been allowed to stand for almost 2,000 years, and yet no one queried it. Maybe this is because Aristotle's theory seemed to closely reflect our everyday experience. There is supposedly no force acting on the arrow as soon as it leaves my hand. But why does it continue to fly in the air? In accordance with Aristotle's theory, a force must have been acting on the arrow, and the only probable explanation that we come up with will be something like this. The arrow continues to go forward because air is pushing it from behind. This, unfortunately, is unjustifiable. Why is it that a cup of water can skid on a Vaseline-coated surface for a long time as soon as I release it from my hand? What is the role of the Vaseline? There is only one reason for this. That is, Vaseline reduces friction, and so once a body is set in motion, it can maintain its motion without needing further any external force. An object at rest will remain at rest, and an object in motion will remain in its state of uniform motion in a straight line. This property of matter is called inertia. The object will eventually stop because the friction between the surface and the object is not zero or negligible. In other words, an object stops mainly because of friction and air resistance. When there is no external force, an object that is in motion will remain in uniform motion in a straight line. And when it is at rest, it will remain at rest. This sounds irrational, but is absolutely true. The first person to discover the law of inertia was, however, Galileo, not Newton. He conducted an experiment like this. He made use of a ball and two smooth inclined planes. The ball was started at a certain height on the left incline. The ball rolled over to the right incline to the same height, no matter how the inclination of the right incline was readjusted. If the right incline is gradually leveled, the ball will likely travel a further distance. If the plane is completely lowered to a horizontal position, the ball will continue rolling in a straight line. This means that even without the influence of any external force, the ball will continue in its state of motion, moving at a constant speed in a straight line. This is the law of inertia. Through insight and hard work, Galileo was the scientist who first formalized this concept. Subsequently, Newton refined and incorporated Galileo's law of inertia into his first law of motion. Galileo died in 1642, the year Newton was born. What a coincidence! At the equator, the Earth rotates at a speed of about 1,700 kilometers per hour. If a ball is thrown vertically upwards in this situation, the ball should move backwards and not fall back into my hand. How can the law of inertia help to resolve my query? A train is moving horizontally at a constant speed of 60 kilometers per hour in a straight line. I am inside the train, and I throw a ball upwards. The ball will naturally fall back into my hand. Let's consider the matter from a different angle. Assuming I am an observer from outside the train, what I see is that the me that's inside the train is moving forward at a speed of 60 kilometers per hour, and so is the ball. This is inertia. In addition to a vertical motion, the ball also has a uniform forward motion, which is the same as the train's. So an observer outside the train will see that the ball is moving in a parabolic trajectory. While on the train, both the ball and I are both moving forward at the same speed of 60 kilometers per hour. This is why after the ball is thrown upwards, it will fall back into my hand. My query is finally solved. Because of inertia, things on the Earth, such as air and hot air balloons, are all moving at the same speed as the planet itself. So the idea of moving westwards is just illusory. How can I hit the ball over to that hillside far away? To get the ball moving at a high speed from a stationary position, it seems I would need to apply considerable force. According to Aristotle, objects can only maintain its motion under continuous application of force. The faster the motion, the greater the force. This is clearly a fallacy. It contradicts the law of inertia. According to this law, as long as an object is moving in a straight line at constant speed, an external force is not necessary. Let us examine the law of inertia from another point of view. Unless acted upon by an external force, an object will maintain its state of motion. In other words, when there is a change in an object's state of motion, that is, when its speed alters, it must have been acted upon by an external force. A force cannot maintain the constant linear motion of an object. A force can change the state of motion of an object. In physics, a force is an action which causes the change of motion of an object. Newton's second law of motion is force equals mass times acceleration. To understand Newton's second law, we first have to understand what acceleration means. When acted upon by a force, an object's speed changes. Therefore, the motion in which an object changes its speed is called accelerated motion. A force causes an object to accelerate. When we drop a ball, it starts falling from zero speed. Due to gravity, it will fall faster and faster. It descends vertically with a downward acceleration. If we use stroboscopic photography to take shots of the trajectory of the free fall at the rate of 1 shot per second, the data we get would be like this. Starting from zero at rest. At 1 second, distance descended 5 meters, speed 10 meters per second. At 2 seconds, distance descended 20 meters, speed 20 meters per second. At 3 seconds, distance descended 45 meters, speed 30 meters per second. The acceleration of a free fall is 10 meters per second squared. In this case, acceleration is the change of speed in 1 second. To reiterate, force causes acceleration. An object is spinning around at constant speed. Nonetheless, we get the impression that a force is at work to maintain the motion. Why? Velocity includes speed and direction. Even though the speed doesn't change, but if the direction changes, there will be acceleration. The Earth rotates around the Sun. As it moves in a circular path, the Earth is constantly changing its direction. Its speed also changes, and it proceeds in an accelerated motion as a result of the gravitational force of the Sun. This is our first conclusion. The greater the force applied to an object, the greater its acceleration. This means that force is directly proportional to acceleration. The second law also relates to mass. For example, to generate the same acceleration, a greater force would need to be applied to a large-sized bowling ball than one smaller in size. The greater the mass of an object, the larger the amount of force is required to accelerate it. This also means that force is proportional to the mass of the object being accelerated. Newton's second law can be summarized as follows. Force is proportional to the product of mass and acceleration. Mathematically, the law can be expressed as force equals mass times acceleration. The story isn't over yet. There is still one more thing: gravity. Aristotle said, "The heavier an object is, the faster it will fall." Many people don't feel anything wrong with this idea because a coin, for example, obviously falls faster than a feather. But Galileo disagreed with this. No matter how heavy or light they are, all objects fall at the same rate. A feather seems to fall at a slower rate because of greater air resistance. However, both the feather and the coin will fall at the same rate in a vacuum. It has been proven that if we take away air resistance, all objects descend at the same rate. To drive a golf ball over to the hillside far away, the ball needs to be accelerated at high speed from a resting position within a short time. According to Newton's laws, a very large amount of force is required. Other than force, What else is missing?